Alrighty, welcome everybody to another midterm review. My name is Zach, TA, you know the whole drill. It's the third time we're doing this. So you have your next midterm on Wednesday, right? I used to try to do these on Monday, but literally every room that could hold more than 75 people was booked at pretty much every hour on Monday. So this is what we got. Thank you for coming. And to give a little bit of a, kind of hate that echo, but that's okay. Let's see if I can turn that down really quick. Is that any better? Nope. Testing. Can you guys still hear me? Is that a yes? Back there, can you hear me? Okay, cool. All right, much better. So this is your eigenvalues test. There's the biggest thing about this exam is eigenvalues, eigenvectors, and diagonalization. I'm sure we're going to talk about that from the ground up. Like your first exam, it was your solution set and your spans. Your second exam is your columns, your nulls, your ontos, and your one-to-ones. And this one is your eigenvalues exam. Okay. Same sort of format you've had for your last couple exams. About 7 questions, some true or false, some short answer, handful of longer questions after that. Okay. Any questions about any of that? Cool. Yeah, hopefully y'all know the drill by now. So, alrighty. Starting off, what questions do we have? Remember, these things can be anything as specific as how do I find an eigenvalue and an eigenvector? To can you do web work question 3, problem 2b? Any of those are fine. If you have something specific you want to ask it. If you have something general you want to ask it. So, questions? Yeah. There's no quick way to tell. Yeah. So to talk about invertibility, though, just in like a whole, invertibility implies you can undo something. Okay, that's the whole point behind it. So, why isn't this mouse working? There we go. So to talk about an invertible matrix, we've talked about this before, something that's being square onto an one-to-one, has a pivot in every row or column. If you want to row reduce a matrix to see if it's invertible, you can do it like that. You want to just tell if it's invertible or not. The other big thing that we've learned since the last exam is something called a determinant. Think that's how you spell it? No, I don't think that's how you spell it, but that's fine. I'm not here to do English. Okay, a determinant, the root of that word is determine, right? What does a determinant determine? Anybody? Somebody with confidence? Yeah. It determines if your matrix is invertible or not. Okay, that's the whole point. If your determinant is 0, you have determined that this is not invertible. If your determinant is anything but 0, you have an invertible matrix. Okay? Or invertible transformation, depending on the context of what we're talking about. There's a couple ways to find a determinant. Some easy, some not. Some get really complicated fast. I personally don't like the method of row reducing and changing the determinant like that. I much prefer cofactor expansion. And I'm sure we'll get to a question where we do it, but for example, if we have a 3x3 matrix, and we're looking to find the determinant of a matrix, what we do is we pick a column or row that we think is easy. What that means is it has lower numbers, whole numbers, or a bunch of zeros. And then we work our way across that, we build our way out. So I guess I'll work in just like a very quick example. That'll make easy. Okay. So, for example, we have a matrix like this. Which column or row looks easy? The second column, right? We have 2 zeros there. So to find the determinant of this, okay, what we do is we first, again, pick our row or column we think is easy. And what I do is whenever I have anything bigger than a 2x2, I draw something that I call my plus and minus matrix. But basically, I'm drawing the thing with the same shape, 3x3. I start with a plus in the top left, then I alternate out. Oh, shit. pluses and minuses on alternating diagonals like that, okay? If you were to look at the actual equation, it would look like -1 to the row plus column. That's a little bit too much math. I just draw my little square with pluses and minuses, okay? So what we do when we find a determinant of a 3 by 3 is we take each of these individual entries and we separate them out. So it'll be -0, +1, -0 again, okay? Now each of these are multiplied by something that we call the minor. And what the minor is it's a matrix composed of all of the values that are not in the row or column of that value. So for example, we're multiplying by the determinant of that matrix. So for this first 0, the minor is excluding that row or column. So what we're left with is 1, 9, 2, 8. Okay. Okay. Now for the next one, we're looking at 1. 1 times the determinant of, what's this matrix going to be? -1, 4, 2, 8. Okay. Do I actually care what this matrix is? Because it's multiplied by 0, right? Okay. So to solve what this is equal to, for the determinant of a 2 by 2, it's major diagonal minus minor diagonal. So this one minus this one. That gets us 1 times -1 times 8 minus 8. So this is -16. So is this matrix invertible? Yes, because its determinant is non-zero. That's how you would check if something is invertible with a determinant like that. Okay. Any questions about this process? This is a very important building block to do anything that has anything to do with eigenvalues, eigenvectors, or diagonalization. Okay. So that's how you determine if something's invertible. Okay. Other questions? Yeah. Sure. Give me a second to pull it up. It said sample midterm B. Another little trick that I think I mentioned last time is I don't think the solutions have been posted yet, right? No? If you go to the URL and then you type at the end of it, before the .pdf -solutions, the solutions will pop up. You said 2B or 3B? 2B, 3B. Just making sure I got it right. Is the one? Is this the right one? That's not it. Sample 3B, 3B. This is not it. You said midterm 3B. Damn, am I in the wrong year? From this year? From this year? Oh, for some reason I can't find it. Could you email it to me? Is it similar to this? Okay. So which one is the because do you see where this is? This is question 3B, correct? Problem 5. That's okay, okay. The whole of problem 5? Okay, that's fine. Why does it keep doing that? Is this the right one? Okay, cool. Yeah, that's fine. All right. So we're talking about complex eigenvalues and complex eigenvectors. All right. So to talk about any of this, let's first talk about what the hell is an eigenvalue. How do we find it? What does it mean? Okay. What does it mean? Basically, all it means is if V is an eigenvector, then it must have an eigenvalue. that instead of multiplying by a matrix, we can just multiply by a constant that we call lambda, okay? To solve for an eigenvalue, it'll always be exactly the same. And I'm pretty sure y'all went over this derivation briefly in class, but if we were to solve for b, we get AV minus lambda v equals 0. A minus lambda factor out of v, but we can't have a minus a number itself, so there's an I in there. It's implicit. Equals 0. So what we're trying to do here is we're trying to find cases where this equation is true. Because we start with this, which is the definition of an eigenvalue of an eigenvector, and we get to here, which is what we're trying to look at. All right. Is the 0 vector ever an eigenvector? No. So our goal is to find out what this vector is when it is not 0. Okay. How do we find a solution set to a matrix equation that's equal to 0? What have we called that in this class? A little bit more confidence, y'all. No, null space, right? Okay. So for something to have a null space, it must have what? A free variable, right? That's the whole like motivation behind a solution set. You have some free variable. So if we have a free variable in a matrix, is it invertible? No. So we have a free variable, then we're not on 2 and 1 to 1, which means we're not invertible because we don't have a pivot in every row and column. If we're not invertible, what is our determinant? 0, right? So what we're going to do first is we're going to look for lambdas to make sure that this system can be solved. And we do that by solving the lambdas in the determinant of a minus lambda I equal to 0, because we want to make sure this is able to be solved. And this is the general way to always find lambdas. Always, always, always. When in doubt, if you take nothing else from what I say, this is like the most important thing about eigenvalues, to find them. Okay? Okay? Once we have found that this matrix has a null space, we call that null space the eigenspace, because that describes our v's that satisfy this equation. So we call the null of a minus lambda I the eigenspace. Okay, and a basis of this is our eigenvectors. Okay, or any vector in this space is an eigenvector, but at the basis of it creates the eigenvectors we care about for like diagonalization when we get there. Okay, so these two things are the most important points I want you to take out of pretty much anything I say tonight about finding eigenvalues and eigenvectors. So now when we look at this question, what we have is we have a equals 5, 5, -2, -1. Find the eigenvalues of a, and then for the with the positive imaginary part, find one corresponding eigenvector. So, well, how do we find an eigenvalue? We take the determinant of a minus lambda I. So a minus lambda I equals 5 minus I, 5, -2, -1 minus I. Not I, lambda. Whoa, I'm getting way ahead of myself. Okay, now we take the determinant of this, and there's two ways to do it. You can multiply things out, AD minus BC, or for a 2 by 2, you will always have lambda squared minus the trace of A, which is the sum of this diagonal. It's B plus 4, lambda, plus the determinant of this, which is -5 plus 10, which is 5. Yes. Okay. Sorry, give me 1 second. I'm gonna make sure I didn't mess up any math. Yeah. It is definitely -4. See, that's why we check things. All right. So, because the trace is 5 minus 1, which is 4, so we subtract 4 lambda. Okay, so this is a quadratic function, right? What we're looking for is we're looking for when this is equal to 0. Is there some general formula that we can use on quadratics to find zeros? Yes. Like for the last exam, you had to remember the unit circle. For this exam, you have to remember the quadratic formula. Okay? And it is always minus b over 2a plus or minus square root b squared minus 4ac all over 2a are the solutions or the zeros to a quadratic equation. Okay? In this particular case, I'm going to skip a little math and just tell you right off the bat that it's 2 plus or minus I. If you want to work that out, you are welcome to. You'll come to the same conclusion. Okay? So to get these eigenvalues, we have solved this equation, which is quadratic, which is again why we use the quadratic form. So these are my lambdas. Lambda equals this. Okay. Any questions so far? Okay. Whatever. So now we have to work to find an eigenvector corresponding to the eigenvalue. Okay. So now we're looking at a minus 2 plus I. Okay, and what we're looking for here is we find, not what we're looking for, we find this is 5 minus 2 minus I, 5 minus 2 minus 1 minus 2 minus I. Okay, so this is a minus lambda I. What did we decide about a minus lambda I from the get-go? How did we pick our lambdas? What is the determinant of a minus lambda I? 0, right? So, is this matrix going to have a free variable? Yes. It's not invertible. It's going to have a free variable. It's a 2 by 2. So how many free variables can we have? 1 or 2, but we have numbers in this one, so we're going to have 1 exactly. Okay. What I mean by that is since we know this is going to have a free variable, and since we don't love doing complex math, what I can do is I can actually just totally ignore the bottom numbers and just turn them straight to 0. Because we know they're similar. We know there's a free variable, and we know our rows are similar. So without having to think about it, we know that we can reduce it. You don't have to know why or how. You know why. Okay. This is only for complex. Well, you can actually do this in general for a 2 by 2 with eigenvalues as well. But now we're looking for the null space of this. You can do this once again by trying to put this in row reduced echelon form, but we're going to have to use again some complex math to get this first number to be 1. Okay. What we do instead is we want to find some vector, because we define the eigenspace as the null space of this matrix, right? So we want this times some vector to be equal to 0. That's how we've defined the null space. That's how the eigenspace. That's how we build out from here. So V has A and B. Okay. And what we're doing is we want this to be true. So we know that we're going to have 3 minus I times A plus B times 5 has to be equal to 0. You can think about some complicated ways to do this. The easiest case to do this is to kind of just flip them backwards. So to make this 3 minus I minus 5 plus, and make B 3 minus I as well, and this positive 5. And what is this going to be equal to? 0. That is because these two sides I have differed by a negative. What essentially that means is if I just want to jump from this step to finding an eigenvector, I switch my two positions, 5 and 3 minus I, and I make one of them negative. And I know when I multiply this together, we're going to get the 0 vector. We know that that will be in our null space, okay? So skipping the steps of actually finding parametric vector form, because we know a lot of things and we're smart at this point. Okay, in linear algebra. Okay, any questions on this? So the answer to this question would be the eigenvalues are 2 plus or minus I. And for the positive eigenvalue, our eigenvector is minus 5, 3 minus I. Okay. I don't know why they stopped. Yeah, go ahead. So if they did ask for the other complex number, the other eigenvalue, if we look back here, this isn't going to be -2 minus I, it's going to be plus I, right? And then this is going to be plus I. And then this would be plus I. So all we're switching is the sign there. So if you're looking for the other eigenvector, what I'm saying here is your other eigenvector for lambda equals 2 minus I, it's going to be -5, 3 plus I. Okay, it's the complex conjugate of what we had for the other eigenvalue. Okay, complex conjugate just means flip the sign of the imaginary part. Okay, yeah. No, you can pick either one. Yeah, for instance, this would also be a valid solution. It's just as fair. Okay, that makes sense? Cool. They didn't ask. In this case, find one for the eigenvalue with the positive imaginary part, find one corresponding eigenvector. Yeah. Cool. Any other questions on this first part? Yeah. Yes. So, do you understand how I got these matrices, right? Just subtract, or to here. Okay, got it. So, erase those again. Just to go over this again, because this is something that is very complex to understand. Okay. We defined this matrix to have a determinant of 0 for a minus lambda I, right? That's how we picked lambda. Okay. So that means this matrix is not invertible, which means when we row reduce, we're going to get a row of zeros, right? So if I know I'm going to get a row of zeros, I know that I can just kind of move a step past this. And I don't have to tell you that it's row 2 equals row 2 times, it's times like some kind of like 1 plus I, something gross that's like messy and a headache to think about. So that when we don't have to think about that, we know that it's going to have a row of zeros, so we can just jump straight to it. Okay, that's how we get to the next step. And then what we're looking for is we're looking for an eigenvector or a vector when we multiply by this matrix, we are equal to 0, right? So we're going to have some matrix with entries, we'll call them x1 and x2. Okay, where we have x1 times 3 minus I plus x2, 5 equals 0, right? Just by doing some matrix math, and then we also know that if we were looking at the bottom row as well, 0 plus 0 is going to be 0. So we're looking for the solutions for this to be true. The easiest way to do this is to make this number this part, and to make this number this part, but make one of these negative instead. So it's like 2 times 3, 2 times 3 times -1. Okay, or it's like 6, -6. Those cancel to 0, right? This is just a more complicated form that looks like that. So we're looking for something that is 5, 3 minus I, plus 5, 3 minus I. But this would get us something that's doubled. What we want instead is we want one of these to be negative. So then they cancel out exactly, right? Because this is the exact same term. One's a plus, one's a minus. So they're going to cancel out, right? So that's why I can just pick, this is my x1, this is my x2. Does that make sense? Wonderful. Okay. So again, that would result in -5, 3 minus I as our eigenvector, x1 and x2. Cool? All right. Now for part B of this matrix, okay, or B of this matrix, part B of this question, okay. Looking here, we're going to do some cofactor expansion, all right. The reason we need to be smart with this is we can do many more computations than we need if we're not careful with the columns or rows we pick. So looking at this matrix, we're looking to find values of C such that the determinant of A is equal to 4. Which of these columns or rows looks the easiest to move down or across? Third column, right? So once again, I'm going to draw my pluses and minuses. Plus, 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 minus, 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 plus, 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 minus, minus, plus. Okay. So what I'm going to get is we're talking about this column. So it's going to be plus 0 minus c times the determinant of, well, what's not in line with c? 1, 2, 3, 3, 0, 4, 1, 0, 1. Okay. And back looking at this column, plus 0 minus 0. Okay. Now, how do we find the determinant of a 3 by 3? Once again, the cofactor expansion. What's the easiest row or column in this matrix? Second column. Boom, perfect. So, again, all the zeros we just ignore. Plus 0, minus 0, it doesn't ever change anything. So we have minus c. I'm going to put a big, no, let's not use those in this class. Big parentheses. And once again, I have to draw my pluses and minuses. Whenever you're taking a determinant, doesn't matter how many steps you go, each time you look at a new matrix, you have to draw that, okay? It doesn't carry from the last one to the current one. So we have minus 2 times the determinant of 3, 4, 1, 1, plus 0 minus 0. So we have 2c times 3 minus 4, which is equal to 2c times negative 1, which is minus 2c. And the question asks, what values of c make it such that the determinant is equal to 4? What value of c does that? Negative 2. Cool. This question looks scary. It's really not too bad. You just have to be careful which rows and columns you pick. And don't overthink it. Okay. All right. What other questions do we have? Yeah. You will get exactly the same answer. Where do you get a column of zeros? Oh, if you pick here, you're going to get it. Are you moving across the column or row? So you're saying if we, which column or row are we moving down or across? Yes, but that would only be for this c, right? So yes, the determinant of that would be 0. But whichever column that c is in, we now have a 2 to consider and a different 2 to consider. And each of those minors are going to have a c in it, and we'll be able to go from there. Cool? Wonderful. So again, it doesn't matter which column or row you pick. It might seem like one is easier than the other, and either way, you're going to get the same answer if you do it correctly. Okay? Yeah. Say it again. How did we know there was a row of zeros? We knew there was a row of zeros here. God, there's so much shit on this page. We knew there was a row of zeros here because we're row reducing, right? And we know the determinant of a minus lambda I is 0. And if we know the determinant is 0, we know our rows are similar and our columns are similar, right? So if they're similar, we're going to be able to row reduce to a 0 row. So without having to think about, you can sit on this and try to think about exactly which numbers we can multiply by to get us to these values, but they're not easy to consider. Okay, does that make sense? It's just kind of like, yeah, it is what it is. We move on, which isn't super satisfying, but you just have to know it. Okay. All right. Other questions? Yeah. No. But if it's bigger, you don't know which row can become zeros. Okay. If it's a 2 by 2, you know the 2 rows are similar. If it's a 3 by 3, the 3 rows are similar, but maybe rows 1 and 2 are actually similar and the third row isn't. You would have to actually row reduce. You're not going to be asked that. Yeah. Oh, yeah. The one I accidentally posted? Oh, Any other questions on this? Yeah. 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 When I draw this box, I just think this is easier. Cool? All right. Moving back to this question. This question talks about diagonalization. Diagonalization is the big culmination of what eigenvalues and eigenvectors are. Okay? There are a few things that we have to talk about before we talk about diagonalization. So talking about the characteristic polynomial, which is what we define as the determinant of a minus lambda I. Okay? This is we just call it the characteristic polynomial. The same way we call the null space of a minus lambda I for a given lambda the eigenspace. Kind of saves words. Okay. So when we do that, we get a general polynomial for any given matrix. Okay. And by the fundamental theorem of algebra, which for those of you that don't remember what that is, for an n-degree polynomial, you will always have n complex zeros, real or imaginary. Okay. If my polynomial expands out and the highest power is negative lambda to the 7th, you will always have 7 zeros to that equation. What they are is hard to find, but you know they exist. Okay. What that tells us is that any polynomial expanded out can always be lambda minus x1, lambda minus, oh, that's not a lambda, that's just next. Lambda minus x2 times dot 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 times lambda minus xn. Always. We can always factor it out like this. But there can be repeats. Maybe x1 and x17 are the same. Okay? And in this particular case, that happens. We have something that happens multiple times, but instead of writing it out, we use squares and powers to shorthand it. Okay, that's the whole point. What that doesn't mean is that, no, I'm not going to say it like that. That's a little confusing. So how we write that is this equation is actually lambda minus 5, lambda minus 3, lambda minus 3. Okay? So I did this with my studio, and it was surprisingly quiet when I asked. But what exactly is algebra? No, actually, what does algebra talk about? Yeah, no, you're in my studio. You know the answer. What is algebra? Yeah, what is it? Oh, I thought your hand was up. Sorry. Yeah. A little bit more specific. What are we talking about with algebra? Numbers. We're talking about numbers. Algebra is the study of numbers, what possible numbers we can have for an unknown variable, right? Numbers themselves, a space is not an algebra, okay? If we're talking about a space, what do we call that? Geometry, right? So that's the difference between algebraic and geometric multiplicity. Algebra is number. Geometry is space. It is amazing to me every year how many people get those two mixed up. You tell me that the number 4 has a geometric multiplicity of 6, and I don't think the number 4 can span 6 dimensions. Doesn't make sense. Separate things. Keep them separate in your head. Eigenvalues are going to have algebraic or geometric multiplicity. Yes. I am in a moment. Eigenvalues, do they have algebraic or geometric multiplicity? Algebraic, because they are numbers. Okay? So we define multiplicity as how many times they pop up in this polynomial. Okay? So in this case, when we're solving this equal to 0, we have lambda equals 5 with a multiplicity of 1 and 3 with a multiplicity of 2. And what that is how many times it pops up in my characteristic polynomial. Okay? Following so far? Cool. Algebraic multiplicity defines the maximum size of my geometric multiplicity. Okay? If lambda equals 5 has an algebraic multiplicity of 6, what is the greatest dimension of my respective eigenspace? Must it be 6-dimensional? What dimension must it be at least? 1. These are important things to know, okay? For example, if I have, in this case, I have 5 multiplicity 1. What is my geometric multiplicity for that as well? 1. Now I have 3 multiplicity 2. What is my geometric multiplicity? 1 or 2. We don't know. Okay, that's the big part of this, is not knowing and what is going to tell us that. Okay, that's a big question that we have to consider, and how we move forward from that is the math of linear algebra. Okay? What space are we talking about that doesn't have any space? Right, that's the motivation there. To have a space is to have a dimension, and geometric multiplicity, I'll actually write this out. So I'm not going to write out all the words. Algebraic multiplicity is the power of that eigenvalue in the characteristic polynomial. Geometric multiplicity is always equal to the dimension of our eigenspace, which we define as the null of A minus lambda I. Okay? And what is the dimension of a null space equal to? It's equal to the number of free variables in that matrix, and that matrix is A minus lambda I. So if I were to ask you, how many free variables does A minus 5I have in this particular question? How many free variables does A minus 5I have? 1, right? Because we have an algebraic multiplicity of 1, so our geometric multiplicity must be 1 as well. Likewise, how many free variables we have in A minus 3I is either 1 or 2. We can find how many free variables we have. That's how we tell geometric multiplicity. Okay? That's how that all works, okay? So, looking at this, once again, lambda equals 5 has an algebraic multiplicity of what? So it has a geometric multiplicity of? So its eigenspace has a dimension of? This is true. Cool. If the 3 eigenspace is the xy plane, what is the dimension of the 3 eigenspace? 2. That's my geometric multiplicity then, right? It's my dimension, my eigenspace. So, diagonalizable means we have n linearly independent eigenvectors, okay? Diagonalizable means that we can write A as C, D, C inverse, okay? So where C is all of my eigenvectors, D is all of my eigenvalues, and they correspond accordingly. So in this case, we have 5, we have 3, and we have 3. Okay? So D will always be able to be filled by the fundamental theorem of algebra. Okay? The question is, can we fill C? That is what diagonalization is. Do we have enough eigenvectors to fill up a matrix with respect to our eigenvalues? So, how do we do this? Well, we know lambda equals 5 is going to have how many eigenvalues? Vectors. 1, a dimension of 1, so this vector does exist always. Okay? We said for lambda equals 3, we know we're always going to have at least 1. But do we know what goes here? No, we have to know that the 3 eigenspace is a plane so that we can have 2 linearly independent vectors. So once again, D is my eigenvalues on the diagonal. C is my they're the basis of the eigenspace for each lambda, okay? And again, to find a basis of an eigenspace, it's just the basis of a null space, which you can do through parametric vector form. You know how to do this. I've seen you do it for 2 exams. I've seen some of you do it. I've seen some of you try. Very few. All right, any questions on what diagonalization actually means? So it means we have n linearly independent things because C must be invertible, right? To have a C inverse. So that's why we can't just fill this with V2 again. No. Because if I plug V2 here, what is the determinant of C? So is C invertible? No. Okay. Okay, looking back here, The 3 eigenspace is an xy plane, so our 3 eigenspace has a dimension of 2. So can we fill up C? Yes. So is A diagonalizable? Yes. All right. So how do we find the determinant if we're given eigenvalues? Yes. I'm just trying to think if I want to show the algebra or not. So the way that we can kind of look at this right here, what if lambda is 0? Then we're solving the determinant of A, right? And this is equal to, this goes away, this goes away. So we're left with minus 5, minus 3 squared. So this is equal to 5 times 9, which is equal to 45. So this is one way to show, but what you need to know is that always, 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 the product of your eigenvalues is equal to the determinant of A. And I know most of you are going to ask me, what is that capital pi? You use a capital sigma in calculus to indicate a sum. You use a capital pi to indicate a product. Okay? It's just the product of all my lambdas. I just don't want to write it out. It gets helpful in certain classes when you have to write like 10 terms multiplied together and you just sum it up in one thing. There's a little I. Likewise, the sum of all of my lambdas is always going to be equal to my trace, which is the sum of my main diagonal of A, regardless if it's triangular, diagonal, anything. Okay. Not going to dwell too much on the algebra of that right now. So my eigenvalues were 5, 3, and 3, and we showed if we multiply these together, we get 45. So is my determinant of A 45? Is A invertible? Yes. Are the columns of A, are they linearly dependent or independent? Independent. What is my range of A? R3. Okay, because it's invertible, we span everything. We're on 2, right? What is the dimension of my null space of A? 0. We have no free variables. We're invertible. These are the kinds of connections that help a lot in true or false questions. Okay, these sorts of like, hey, it's invertible. What does that mean? What does that mean for other things that we've talked about in this class? Yeah. I think that was for just a general case. I don't think we were talking about a specific matrix for that. Oh, we were talking about A minus lambda I. Yeah, A in and of itself, its determinant is the product of eigenvalues. We define the determinant of A minus lambda I to be 0 to find our lambdas. Cool? Yeah. Because my eigenvalues are 5, 3, and 3. We multiply 5 times 3 times 3, it gets positive 45. Cool? Okay. And you can see here that this is positive, positive, and this is squared, so it's positive as well. Yeah. Hmm? So what is always true is for different eigenvalues, the eigenspaces will be different. Always. Because if they were the same, then we would have 2 eigenvalues for the same line. So if I'm on that line, say if my line for 3 and my line for 5 are the same line, and I lie on it, when I transform a vector that's on that line, what do I multiply by? 3 or 5? You can't tell. That's how we build off of this. We know for any distinct eigenvalue, you will have at least one corresponding linearly independent eigenvector. That's a statement you'll hear. And common true or false question is like, given you have n distinct eigenvalues, is A diagonalizable? Yes, right off the bat. If all your algebraic multiplicities are 1, all of your geometric multiplicities are automatically 1 as well. All your algebraic and geometric multiplicities are equal. You can fill up C. Lots of stuff to say yes. Okay. All right. Any other questions so far? Okay. All right. Part 4 here says the homogeneous system given by the equation a minus 3ix equals 0 has two free variables. Okay, what is true of a minus 3i? What is true of this? What do we call the solution set to this equation? Eigenspace. Because 3 is an eigenvalue. That's not true for any number. Okay. This is the lambda equals 3 eigenspace. Okay. And we said lambda equals 3 has an algebraic multiplicity of what? 2. So what must its geometric multiplicity be? 1 or 2, right? So this is saying for our eigenspace of lambda equals 3, must we have two free variables? Must we have a dimension of 2? No. You can, you don't have to. Okay, so this one's false. Okay. Any questions on this? Okay. What other questions do we have? Yeah. Yeah. Okay. All right, so I kind of glossed over complex numbers a little bit. I'm going to talk about them again in a second. But there are 3 cases of things you need to know the determinant of and the eigenvalues and eigenvectors for pretty quickly. Okay. And they are a rotation, a projection, and I said rotation, projection, and a reflection. Okay. So I have to start in opposite order. All right, we'll start by talking about a reflection. For a reflection, if I'm rotating over some line, okay, say this is the line I'm rotating over, okay, there are 2 big spaces to consider, okay? If I lie on this line, what's going to happen when we transform? What's going to happen to the blue line as we flip over the red line? Which is the same as multiplying by 1. So we call this our lambda equals 1 eigenspace. Okay. If something is sticking straight off the line, what's going to happen to it? It's a large room, y'all. Can't hear everybody. It's going to flip over, right? It's going to go exactly to the other side, which is the same as multiplying by what? Lambda equals -1. Okay. Any reflection is always going to have lambda equals 1 and -1. Always. Okay. And you will likewise always have a determinant equal to -1. And as a little sidebar, you're going to have lambda equals 1, multiplicity, n minus 1, n minus 1, multiplicity. Come on. Multiplicity 1. Okay. Because what must my algebraic multiplicity is always sum to? N, right? So what is n minus 1 plus 1? N, just as a sanity check. Do you think we can undo a reflection? Yes. So is it invertible? Okay. What is its determinant? Non-zero. It is -1, which is non-zero, but non-zero is the important part to take out of that. Okay. Is it diagonalizable? Why? It does not have n distinct eigenvalues. What if we're in 5 space and we're rotating over a 4 space? So if we're in 3 space and rotating over a plane, how many vectors are on that plane? How many independent vectors are on that plane? And 2, right? A plane is 2 linearly independent vectors. How many vectors are on the line sticking off the plane? Okay, how many linearly independent vectors are sticking off the plane? 1, right? It's a line sticking off a plane. The plane has a basis of 2 vectors. Line has a basis of 1 vector, right? So our 1 eigenspace has a geometric multiplicity of 2, and our -1 eigenspace has a geometric multiplicity of 1. that follows in a higher dimension too. If we're rotating over a 4 space, there are 4 dimensions in the 4 space. So we have a geometric multiplicity of 4. And for the -1 space, what we're reflecting over has a geometric multiplicity of 1. So 1 plus 4 for my geometric multiplicities is 5. And if our geometric multiplicities add up to n, then it's diagonalizable. That's another way to think about it. You know, those were a lot of high-level words all at one time, so I apologize. But yeah. It's not really something that's going to be asked, but basically what you can think of is there's only like, in any given space, you can only pick one specific part to flip over, right? Like in 3 space, you can flip over a whole plane. In 2 space, you can only flip over a line. In 4 space, you can flip over a 3 space. In 5 space, a 4 space, and so on and so forth. You're always going to be missing one dimension from whatever you're reflecting across. So whatever you're reflecting across always has one dimension, and whatever is sticking off of what you're reflecting across has a dimension of 1, a line sticking off a plane, and then whatever you're reflecting across has a dimension of n-1. You don't need to dwell on that too much. Just know it's diagonalizable. That's a very high-level step that we don't really talk about in this class. Please don't get too stuck on that if you don't understand it, okay? Cool? Okay. A projection. Very similar to a reflection. We have lambda equals 0 and 1. Okay? So if I have a lambda of 0, am I invertible? No, because my determinant is my product of my eigenvalues. If I have an eigenvalue of 0, what is my determinant? 0. So it's fair to say if the dimension of if the 0 eigenspace exists, A is not invertible. Okay? If we have a lambda of 0, our determinant is going to be a bunch of other numbers times 0, which is equal to 0, which means it's not invertible. It doesn't discount us from being diagonalizable. It's just 0 is just a number. It's fine. It's still something to consider in D and C. But it tells us about invertibility itself and only itself. That is the only relation between diagonalization and invertibility, a lambda of 0. To know that tells you a little morsel of information about diagonalization, tells you an eigenvalue, tells you everything about the determinant though, tells you everything about invertibility, okay? So they're like two separate circles on a Venn diagram, okay? So to write that out, the determinant of A is equal to 0. And if we wanted to look at that again, red line. If we're on the line that we're projecting onto, what's going to happen to us? Nothing, right? If we're sticking straight off, what's going to happen to us? We're going to multiply by? Yeah, we're going to get crushed down to 0. Okay. So you're once again going to have lambda equals 0, multiplicity 1, and 1 multiplicity n-1. This is stuff you don't really need to know. And I just enjoy it because I like math. It is also diagonalizable. Not going to try to explain that one. Same exact thing though. Okay. All right. Last one. Well, actually. Okay. Y'all have not heard the word dot product, have you? No. Okay. So, to tell you how to find something that is sticking off of these lines for each of these 2 cases, okay? This is what we're going to be talking about a lot after this midterm, okay? But if I give you a graph, and this is the span of, I don't know, 4, 5, 4, 3, okay? This, and I'm saying that this is a projection onto this line, okay? So this is the line we're projecting onto. This is my lambda equals 1 eigenspace. How do I find my lambda equals 0? How do I find a vector that sticks straight off? Okay. So what a dot product is it something we're going to talk about after the exam. I like to use it for this stuff. There's like 6 different ways to solve it. I think this is the easiest way to find it. Okay. What a dot product is it's a measure of how parallel you are. Okay. How much you're pointing in the same direction. Okay. So if your dot product is 0, how parallel are you? Not, right? So we call a dot product. We literally just draw a dot, and it's dot a vector. We're looking for it to be equal to 0. If you were a 3rd grader and looking at trying to multiply 2 vectors together, how would you think you would multiply these 2 vectors together? 4a plus 3b. That is what a dot product is. Okay, that's actually exactly what we do. We just multiply the things that line up. And we're going to get a measure of how parallel these 2 vectors are. We want that number to be 0, right? So we have an equation now. We can kind of solve this for any general a and b. We can do the same thing we did for complex numbers, where we can flip them and make one negative. So we could make this -3, 4. Or you could solve in general. You can get a equals -3/4 b. And you could pick some value for b and get an a. All right? Either of those are fine solutions. We have 2 variables, 1 equation. We're going to have a free variable. We get to pick one of those numbers. Don't pick 0. It's not very interesting. And also 0 is never an eigenvector. Okay, so all I mean to say by that is either flip them and make one negative like we did for complex numbers, or try to solve this and just once again make it 4 times -3 plus 4 times 3, which is always equal to 0. Flip them and make one negative. That's how you find what this line is. -3, 4. Cool. Any questions on that? Yeah. Yes. Unless it says show your work, and then say, like, I did this because I was looking for something that was orthogonal. Orthogonal means perpendicular in a higher dimension. But yes, we'll talk. It's not something that you'll probably have to show your work for. I wouldn't dwell on it too much. Other questions about this? Okay. All right, last one is rotations. So a rotation will always, always, always have 2 complex lambdas. Okay? Why? Well, what is a complex number? For somebody who I haven't already talked to about this. What does a complex number mean? Okay, real plus an imaginary. Call it a plus bi. What does that mean? What does it mean? I is very real. No, it is imaginary. But why do we want complex numbers? Why is this something that we should even think about? Right? You guys have been taught this. Why would we ever want to look at complex numbers? Complex numbers are what run pretty much any kind of computer or system that uses any kind of signal. And especially as engineers, complex numbers are going to pop up and not stop being there for you. Okay? For those of you that aren't engineers, you got to pass the class. You got to know it. Sorry. What a complex number is it is a number that contains 2 parts. It contains an angle and it contains a magnitude. That's the whole point of a complex number. It gives us a and it gives us b. And it gives us some angle here as well. Okay? So if some system has a complex eigenvalue, that means we're rotating. That's what it means. In a signal analysis, we would use complex numbers to describe signals, and we would multiply these signals together by combining their magnitude and their phase accordingly. That's why we use complex numbers. It's the whole point. It's to be able to combine things. And that's not just signals. That'll be vibrations, or any kind of periodic symbol can be defined as imaginary components. Okay? So that's what a complex number is. So does it make sense that a rotation has complex eigenvalues? Yes, it's going to have an angle. Rotations have angle. Complex numbers have angle. It's the whole point. Okay? So like the one we did earlier, where we had a matrix that we solved for a complex eigenvalues and eigenvectors. That matrix was both rotating and scaling at the same time. Okay. Is a rotation invertible? Can you undo a rotation? Yes. The determinant's always equal to 1. Okay. That's pretty much all you got to know about rotations. Okay, I won't dwell much more on that. So if you're rotating by 40, if you're rotating by 90 degrees, what do you think your eigenvalues are going to be? No. So on a complex, on the unit circle, which way is 90 degrees? Up. If you're talking about complex numbers, which is that I or is that the real part? The I. So if we're rotating by 90 degrees, we're going to have lambda equals plus or minus I, because they come in conjugate pairs. That's how you can read what a complex eigenvalue tells you about the system itself. It's going to be rotating by some amount of degrees. And the one we had earlier, I believe, is 2 plus or minus 1, or plus or minus I. So that means it had a magnitude of root 5 and an angle of the arctangent of 1/2. That's what that is, right? Because this is 1, this is 2. They create root 5. There's an angle there that's arctangent of those two things. That's what complex numbers are. That's the whole point. Okay? Yeah. Haha. If we have 180, what are our eigenvalues? Not 1. -1. Plus or minus I. You can also think of that as flipping over the x, both x and y. -1, 0, 0, -1. Right? If we think like the two-dimensional rotation matrix, and we plug in theta equals -180, this is what we're going to get. Yeah. In 3 space, you can only rotate around 1 dimension at a time. So that's kind of how you have to treat it. Because in your eigenvectors, you'll get complex number, real number, and that tells you which axis you're rotating around, or which vector to some extent. Don't dwell on that too much, but that's how that works. Okay. Any other questions? All right. What other questions do we have in general? Yeah. 5.4 web work, problem 7. Yes, let me pull it up. Okay. Is the right question? Cool. So this one says find a 3x3 matrix A whose -1 eigenspace is this and whose -4 eigenspace is this. And that is a -1. It got cut off for some reason because web work sucks. Anyway, we're looking for this to be true. We're looking for an A. So we're given eigenspaces. So how do you think you would go backwards from an eigenspace to A? Through diagonalization is how we do it. Diagonalization is also called eigendecomposition, which I think we should call it, but we don't. I don't teach this class. But the whole point of diagonalization is to decompose in terms of the eigenvalues and vectors. Okay. So what we're going to have is we're going to try to build a C and D for this system. Okay. What do I know? Which eigenvalues do I know I have? Well, it gives me -1. It gives me 4. So I'm going to go ahead and start filling this in. We have a -1. We have a -4. What goes here? We don't know immediately. We're going to have to look into it a little bit more. Okay. C is our corresponding basis for each eigenspace, right? So let's talk about the -4 eigenspace first, just because it looks easier. What is a basis for this space? -2, 0, -1, right? Okay. So far, so good. Make that a little clearer. So that's my vector that corresponds to lambda equals -4. Now let's talk about lambda equals -1. Talking about this space. All right? Now that's a weird equation. It randomizes the numbers, so sometimes it gets particularly weird. This is one of those times. So, here's one eigenspace is the following. What does this equation look like to you? What kind of space? Null space. We have a bunch of stuff equal to 0. Okay? So we can talk about this as the null. Oh my god, why is my Apple Pencil fucking up? Of 1, 0, 0. Okay. How many free variables do I have? 2. What is the dimension of my eigenspace? 2. So is this going to be diagonalizable? Yes. My geometric multiplicity is 2. What does my algebraic multiplicity have to be at least? 2. So that's how we know we can fill in that extra box here. Because as we know it has an algebraic multiplicity of at least 2, because it has a geometric multiplicity of 2. Okay? And the other one's also already filled. So how do we find these vectors? Well, how do we find the base of a null space? Parametric vector form, right? This one is particularly easier. We're going to get x2 times 0, 1, 0 plus x3 times 0, 0, 1. Cool. Do we know C is invertible? Don't think about it. Yes. Why? Because it's a diagonalization. We design a diagonalization for C to be invertible. That's the whole point. So you don't have to think about it. I mean, I could ask you what determinant is. You can tell me it's -2 as well, because it's triangular. Not the point, though. You will always, if you have found C, it will be invertible, or you will not be able to diagonalize, because you have a C inverse. How are you supposed to find a C inverse if C isn't diagonalizable or invertible, right? Yeah. Okay. Well, we go from here to reduced row echelon form. 1, 3, 0. We get x1 equals -3x2. We get x2 equals x2. We get x3 equals x3. So our vectors are then -3, 1, 0, 0, 0, 1. Right? It's designed to be diagonalizable in this case. I'm not going to spend my time inverting a 3 by 3 and then multiplying 3 by 3s out. But you can solve A equals C, D, C inverse. For this exam, most of the time, it'll just, if you have a diagonalization question, it'll just ask, give C and D. It's not very interesting for the graders to watch you multiply out 3 by 3 matrices, okay? It'll be very clear in what the question is asking. It says, list C and D. You usually don't have to list C inverse. If you do, it's probably 2 by 2, and it's easy anyway, so who cares? Okay. All right. Any other questions? Yeah. From where? This -1? Yes. So the free variables in that null space define my geometric multiplicity. Okay? And my algebraic multiplicity must always be greater than or equal to that number. So we had 2 boxes filled already. And it could have a maximum of 2 spaces to fill. And we know it has 2 vectors, so it must have 2 columns in D as well. It's kind of how you can think about that. Cool? Cool. Yeah. No. As long as your columns line up, it doesn't matter. So like if I wanted to move this to the 3rd column of both of these, that's fine, as long as I move this over here. Okay? And that's why in web work, I think there was one where it said you'll get partial credit, and it was like a CD question. And if your D was right, but your C wasn't, it would mess up. Because web work was actually checking if you were right by multiplying C times D times C inverse. So it was just wrong, because there's not an infinite number. There's n number of possible D for distinct numbers, right? So yeah, you get what I'm saying. Cool. Other questions? Yeah. Okay. Yeah. You have to find the inverse of a 3 by 3. You look at it and you get really sad for a second. And then you start solving. So, if you have to find the inverse of any matrix in general, this is actually true for a 2 by 2 as well. So if you're stumped, this method will always be true, okay? We must always have A inverted with I, or not inverted, augmented with I. In general, for any square matrix A. This is where we start. So for example, for a 3 by 3, it's going to be a 3 by 6. Okay. If A is invertible, what does A in reduced row echelon form become? The identity matrix. As we do this, A inverse is going to pop out over here. That's how you do it. You have to do the row reduction of a 3 by 6 matrix, which isn't impossible. It's just a headache. Okay. So again, not impossible, just a headache. So I took a bunch of like mechanical engineering and robotics classes in my undergrad. And for what, like, eigenvalues are probably the most important thing to take out of this class, by the way. Like, for real. These are the thing that engineers use a lot of. There's all kinds of different things that engineers pull from these classes. For things where you're solving a lot of differential equations with multiple variables, eigenvalues are the things we talk about, okay? In computer science, we use eigenvalues for all kinds of different quick computing processes and all kinds of other stuff. It pops up a lot. In one of my classes, they gave me a 5 by 5, and they said, find the eigenvalues and eigenvectors in a 4,000 level class, and it was so sad. It took me so long because it was in like an exam, and it was a 5 by 5 fully filled matrix. I had to find 5 by 5 null spaces, just miserable. But it happens, and we know how to do it. It's not hard. It's just shitty. So, any other questions? Yes. The worksheet from today's studio. Sorry, which problems did you say? Question 2. No, this doesn't look right. The one about complex eigenvalues? Yeah. Okay. Also, one more note to all y'all. There's only one more studio in the semester. We're almost to the end. So this is the time to get very serious about the stuff we got going on. What's up? What? Okay. I'll talk about that after I stop recording. Oh no, that's not the right thing. Okay. This question asks to find all eigenvalues and eigenvectors of the following matrix. Okay. So for a 2 by 2, what will always be the case is you'll always have lambda squared minus the trace of A times lambda plus the determinant of A. You can work out A minus lambda I and factor it out, but regardless, lambda squared minus 2 lambda, in this case, this is plus 5. Okay. From here, how do we solve a quadratic equation equal to 0? Quadratic formula, right? So we get 2 over 2 plus or minus, oh, that just looks like a 1. Plus or minus square root of b squared minus 4ac all over 2a, which gives me 1 plus or minus 2i. Okay, that's our eigenvalues. How do we find our eigenvectors? Well, we find the null space of A minus lambda I. So we'll do just lambda equals 1 plus 2i first, where we have 1 minus 2i, 2 minus 2, 1 minus 2i. This gives us minus 2i, 2 minus 2 minus 2i. See, this is a case where it's not ridiculous to find out how you can combine rows. You can multiply this bottom row by I, and then they're similar, and then you can combine them. But we also know that this is A minus lambda I, so it's going to have a 0 row when we reduce. So we're going to skip the steps, 2i, 2, 0, 0. And the eigenvector will always be the flipped numbers, 2 negative 2i, and we flip the sign of one of them. Okay. So that's how we got our eigenvector. And then for lambda equals 1 plus 2, minus 2i, we don't have to do really any extra work. We just take the conjugate of 2i. Take the conjugate of this, which is what that little star means, which is 2 minus 2i. We just make all of the imaginary parts flip sign. Okay. Cool? Okay. Any other questions? Take one more. Yeah. Yes. So if you are given 3 points and you're asked to find the area of the triangle between them, you will always have, we'll call it 0.1, 1, 1, 0.2 equals 3, 4, 0.3 equals 5, 5. Okay. The process will always be the same. Okay. We must first find vectors between these points. So the way that we do that is we kind of shift everything back to the origin, and then we talk about them. What I mean by that is we just call vector 1 0.3 minus 0.1, and when we call vector 2 0.2 minus 0.1. We're just subtracting any two vectors. We just have to make sure that these two equations between the two vectors aren't the same thing. Okay, they're not both 3 and 2. Maybe one's 2 and 1, and one's 1 and 3. Some kind of something like that. Okay. So in this case, it's gonna be 4. Oh, that's not 44. 4, 4. And this is going to be 2, 3. Okay. So now these are actual vectors. And what we do is to find the determinant, if I draw this on a graph, two, 3, 4, 4. Okay, the triangle would be this triangle here. Okay, but we can't find that so easily. But what we can find is the area of this parallelogram. And to do the full area of this parallelogram is the determinant of v1, v2. That's how we define it. Okay, so this is, what were they? 4, 4, 2, 3. Okay, so the determinant of this is 12 minus 8 equals 4. So that's this total area. So how do I find the area of just this part? Well, it's just half of it. So this just becomes 2. Another quick important note is, can we have a negative area for the sake of argument in this class? No. Volume? No. We can't have a negative area of volume for the sake of argument in this class. Okay. Cool. Any other questions on this? All right, wonderful. Where does my mouse keep going?